All right, this is chapter 4, sample test I gave you. Write a polynomial function that looks like this graph. So the things we notice is it looks like it hits at about +1, and it hits at us as a bounce, so it has multiplicity. This is the root, or the 0, is 1, and a multiplicity of 2 because of the bounce. And it goes kind of straight through at -3, so that's a root. But since it just goes straight through, it has multiplicity 1. And so this could be a third degree, and it has 2 curves, so degree 3 is appropriate. So we think it's x minus 1 twice, and an x plus 3. And it might have a number times this. Now I notice one thing else, it looks like it goes through -1 as a y-intercept. So if I put in 0 for x into this, I get something that should be here times 0 minus 1 is -1 squared is 1, and 0 plus 3 is 3, and we want that to come out to be -1 for the y-intercept. Well, this something then, 1 times 3 is 3. If we divide both sides by 3, this constant has to be -1/3. And so we get -1/3 times x minus 1 squared times x plus 3 would look something like this. Let's see how close that does look. So we'll go here just to make sure we're doing this right. Parenthesis, -1/3, 1 divided by 3, close parenthesis, times parenthesis, x minus 1, close parenthesis, squared, times parenthesis, x plus 3, close parenthesis. I'll do zoom 6. Oop, did I forget the minus? -1/3 x plus x minus 1 squared and x plus 3. Graph. Oh, yes. So it looks like it comes down through 3. It goes down 1, 2, 3, or 4. This looks like somewhere between 3 and 4. It comes back up through 1 and hits -1 on the y-axis, and it's up there. Let's go zoom decimal, and you can see it went through -3, went down below 1, 2, 3. It's a little bit more than 3. The graph over there looks like a little more than 3. Comes back up through -1 on the y-axis, hits at 1, and then continues down. Now I could multiply this out. See, x minus 1 times x minus 1 is x squared minus 2x plus 1. I could take that times x plus 3. That would be, I'll do that over here. That would be x times all these would be x to the 3rd minus 2x squared plus x. And then the 3 times all these would be 3x squared minus 6x plus 3. So I'd have x to the 3rd plus x squared minus 5x plus 3. Then I could take all of that times the -1/3 and come up with another name for this would be -1/3 x to the 3rd minus 1/3 x squared, and then plus 5/3 x, and minus 1/3 times 3 is -1. So there's both versions of it. This is fine for what I want you to be able to interpret from the graph. Okay, number 2. Number 2 starts, let's see if that's lined up for you. Yeah. So we have this fifth degree polynomial. And the way I would start this one is I would start by graphing it just to get an idea of what the zeros might be. X to the fifth plus 4x x to the fifth plus 4x to the fourth plus x to the third minus 2x squared, subtract 12x, subtract 72. Zoom 6 ought to be a decent window to look at this with. And we see a bounce at -3 and going straight through at 2. A bounce at -3, -3, so that's the root with a multiplicity of 2, and then straight through at +2, so we have a root of 2 with a multiplicity of 1. That would be 3 roots. Multiplicity is how many roots? 2, 3, and there should be 5, so there might be 2 imaginary ones. Now to get to those, we would have to factor this, factor out, see if the root's x is a -3, that means the factor is x plus 3. We think that's a factor twice. We think +2 is a root, so x minus 2 would be a root once, a factor once. So f of x in factored form would have this, and there's something else here. And to get to that, I'm going to use synthetic division. I could use long division and divide x plus 3 into this and then x plus 3 into this. But I'm going to do the synthetic, which means you take the root, the -3, and put it into, synthetically divide it into this by putting down the coefficients. There's 1 x to the fifth. There's 4x to the fourth. If we were missing x to the thirds, I'd have to put 0, but there's 1x to the third. There's minus 2x squareds. There's minus 12x's, and then a minus 72. And to do synthetic division, you add 1 plus nothing is 1. You multiply the -3 times the 1 is -3. You add, you get 1. You multiply, you get -3. You add, you get -2. You multiply, you get 6. You add, you get 4. You multiply, you get -12. You add, you get -24. You multiply, you get positive 72. You add, you get 0. So that went in evenly and left me with, this was x to the fifth, so this is 1x to the fourth plus 1x to the third minus 2x squared plus 4x minus 24. But I don't need that because I'm going to divide it, the other x plus 3 in by putting the root, -3, into this and just continue on. So 1 plus nothing is 1 times -3 is -3. 1 plus -3 is -2. That's plus 6. That's 4. -12. That's -8. -3 times -8 is positive 24. Adds to be 0, which is what we suspected. So now we've confirmed that that's there, and we've got what's left was x to the fifth, x to the fourth, 1x to the third minus 2x squared plus 4x minus 8. So we're reducing this. We're slowly getting it down. Now the x minus 2, which has a root of 2, so we put the root in. 1 plus nothing is 1 times 2 is 2. That's 0 times 2 is 0. 4 times 2 is 8. 0. Went in evenly. So this was x to the fifth, x to the fourth, x to the third. So this is 1x squared plus no x's plus 4. So what's left out here is x squared plus 4. Now, if I were trying to find out what makes that be 0, I've got several routes I can go. One is to take the calculator out and just use the quadratic formula. Program. Let's see here. Quad form is mine. Enter. Oh, this one has a problem in it. Let's see, 2. Oh, I got answer to program, so clear. Program. Quad 4, where is that at? Right there. Enter. Enter. What's A? We have 1x squared, no x's, and then plus 4. Enter, and it says a non-real answer. Now, I can fix that. I can push mode on my calculator. I'm going to quit, push mode, and say, well, do complex answers by saying, instead of just real answers, do A plus BI. Complex answers. I press enter and I quit, and I can just press enter, run the program again. A was 1, B was 0, C was 4. It says, oh, you want the non-real answers? 2i and negative 2i. So I have imaginary roots of 2i once and negative 2i once. Now, I could get those without the calculator program, which some of you may not have, by just solving this equal to 0. X squared plus 4 equals 0. This is simple enough that you can subtract 4 and get x squared equals negative 4, and take the square root of both sides and get x equals to the plus or minus the square root of negative 4. The square root of negative is I. The square root of 4 is 2. So I got plus or minus 2i. So I get the same answers there. Or I could put this into the quadratic formula using 1 for A, 0 for B, 4 for C, and I would get these same answers. Okay? So, determine the roots, real and imaginary, and their multiplicity. That's that answer. But we've done a lot more. So the rest of this should be easier. Determine the behavior of the function at the zeros and explain the implications of that behavior. Okay, well, we graphed it and we found that the behavior at negative 3 was a bounce, so that implies that it's a multiplicity 2. And the behavior at 2 was straight through, so that means that it's multiplicity 1. So negative 3 has multiplicity 2, and 2 has multiplicity 1 because it went straight through. I'm just writing big so you can see it. And this one was a bounce. Okay? Determine the Y-intercept. Well, that's pretty simple. You put 0 in for the x, and all this x's wipe out all that, and you get negative 72. 0, negative 72. Describe the end behavior and explain. Well, since it's a degree 5, it has to go opposite, one end going up and one end going down. And since it's a plus on the beginning, on the x, the highest degree, the positives are going to go positive and the negatives are going to go negative. So down for negative x on the end, and up for positive x direction. Okay? And you can write that in words. Again, I'm writing this big so you can see it. Determine the points of local maximum, if any. Well, in this particular case, if I look at the graph again, this goes up and then down and up. And so there's a local maximum right there at where it bounced. And it's at, the maximum is 0 and it happens at -3. The maximum, the local maximum, is 0 at x equal -3. Now if I had to find the local minimum, which must be down in here someplace, I could do that. It's somewhere between -3 and +2, and so I could go second, calculate the minimum that's between -3 and +2, and it says make a guess. I'll say -1, and it says no, it's at -0.866. Is at at positive 0.866, and the minimum value is, I believe that's 80.5, -80.5. I got pixels that are not working on this calculator. Okay, but I didn't ask for this, but that would be helpful maybe in determining some other things. So I just wanted to show you how to get that. You can also get that local maximum by doing the similar. Second, calculate the maximum and say it's between -4 and -2, -4 and -2, and it's about -3, and it says right on, -3, it's 0. The maximum value is 0 at -3. Okay? Determine the intervals where f of x is positive. This doesn't say increasing or anything else, so positive f of x, f is the y value. For what x's is the y value positive? Or another way to say that is, when is f of x greater than 0? 0 is not positive, it's not negative, so it has to be greater than 0. Well, all of this section, the y values are less than 0. And all these values in here, it's less than 0. But from 2 on, beyond 2, they're positive. And so I'd have to say from 2 to infinity, in the x direction, for x's, 2 to infinity, the y is greater than 0. Okay? And finally, determine the intervals where the function is increasing. Oh, increasing. Well, it increases up till here. So that's for x's -infinity up till -3. From -infinity up to -3, it's increasing. Then it decreases till the minimum spot down there. So it's a good thing we found that. And then from the minimum on, which is at, and remember we do this in terms of the x, from the minimum, which is at 0.866, on, it's going up. And so we have two sections, this section, or for these x's, or for these, because we don't want to look for the intersection of these. We want all of these places, for all these x's, the function is going up, it's increasing, and for all of these x's, it's increasing. All right, that's page 1.